Today we are coming back to microeconomic theory 2.
Today, we continue the game theory with mixed strategy and focal point equilibrium. We use the mixed strategy when there are more than one Nash equilibrium or there is no Nash equilibrium. We solve the game by assigning probability and we find the expected payoffs. Then the equilibrium is at the highest expected payoffs of all players. Now, recall the game number 2, the meeting point, when we have player A and player B, and the strategy is going to university and to the airport. The payoffs are on the screen. If they meet each other, then they will gain 100 U-tunes for both players. But if they don't meet each other, then they will lose 100 U-tunes for both players. Here, we have the reaction function of player A. If player B goes to university, player A will go to university, and then he or she will gain 100 U-tunes. But if player B goes to the airport, then player A goes to the airport too, and he or she will gain 100 U-tunes. So we have two reaction functions of player A. Then we turn to see the reaction function of player B. If player A goes to university, then player B will go to university too, and he or she will gain 100 U-tunes. But if player A goes to the airport, then player B will go to the airport too, and he or she will gain 100 U-tunes. So there are two reaction functions of player B. We compare the reaction functions of both players. So you see that we have reaction function number 1 of player A and reaction function number 1 of player B in the same cell, which is going to university and going to university. This is the first pair of reaction function. And the second pair of the reaction function is at going to the airport and going to the airport. You see that the reaction function of player A is the blue lines and reaction function of player B is the brown lines. So the brown and the blue are in the same cell. Number 2 and number 2 are in the same cell. So this is the second pair of the reaction functions of both players. You see that we can match the reaction functions of player A and player B in the same cell. So number 1 and number 2. So you see that going to the university and going to university, we have number 1 and number 1 stay close to each other, stay together in that cell. So this is the Nash equilibrium. And you see that number 2 is with number 2 in the cell indicating going to the airport and going to the airport. So this is the second Nash equilibrium. So you see this is the situation which have two Nash equilibriums. You see that the Nash equilibrium is the matching between the reaction functions. So if you can find the reaction function number 1 and reaction function number 1 of both players, in the same cell, that is the Nash equilibrium. And you see that we have the relation function number 2 and relation function number 2 of both players in the same cell as well, but elsewhere. That is another Nash equilibrium. So here we have two Nash equilibriums. The first equilibrium, you can see the flow or the continuous relation functions, the matching between them. We can read, if A goes to university, then B goes to university. And then if B goes to university, then A goes to university. And you can repeat this forever. So yeah, it is the flow of the relation functions. So you can match these relation functions, and this is the Nash equilibrium number 1. We have the second Nash equilibrium here. If A goes to the airport, then B goes to airport. If B goes to airport, then A goes to the airport. And you can repeat it. If A goes to airport, then B goes to airport. If B goes to airport, then A goes to airport. And you can repeat it forever. So you can see the flow of the relation functions, the matching between them. Therefore, this is the second Nash equilibrium. Therefore, there are two possible places that player A and player B may meet each other, but we still don't know exactly where they will meet, the university or the airport. Thomas Schelling, he got the Nobel Prize in Economic Science in 2005 for having enhanced our understanding of conflict and cooperation through game theory analysis. He suggested the focal point, and he called it the focal point equilibrium. Unfortunately, he has passed away in 2016. He said that one of the many Nash equilibria might stand out from the others due to some asymmetry that is common knowledge to the players. If the players think the same or know each other, that the other side tends to go to university first and then go to the airport later, or he or she may have some activities to do at the university. Therefore, the choice of going to university stands out with higher probability. So, if we assign the probability, you can see that going to university will have the higher probability, for example, 0.8, comparing to the probability to go to the airport, which is 0.2. You see that the summation of probabilities must be 1. The probability of going to university, 0.8. The probability to going to the airport, 0.2. 0.8 plus 0.2 equals to 1. And we have the probability of player A going to university, 0.9, and then the probability of going to the airport of player A, 0.1. 0.1 and 0.9, the summation is 1. Therefore, you can see that the choice of going to university stands out from going to the airport. Here is the focal point, as suggested by Thomas Schelling. Recall the payoffs. Here you see that if they meet, they will have both 100 utils. But if they don't meet each other, then they will lose 100 utils. Now we calculate the expected payoffs, or the payoffs adjusted by the probability. In economics, when you use the word expected, it means that we have the probability to get involved in that calculation. You must remember this. Expected return is the return adjusted by probability. expected payoffs is the payoffs adjusted by probability. Here we have the probability and we can calculate the expected payoffs of A. If A goes to university, and expected payoff of B if B goes to university. So in this first cell, you see that if player A goes to the university, what would happen? We have the probability of 0.8 that B is going to university too. Therefore, if B goes to university, A will get 100 YouTubes. 100 YouTubes with the probability of 0.8. Therefore, the expected payoffs is 80. So you'll be multiplying the total utilities 100 with the probability 0.8. 100 times 0.8 equals to 80. Look, the payoffs of player A, you must use the probability of player B to calculate because it is not depending on A but B to make that payoffs happen. A will go to university, okay, fine, but B will go to university with just the probability of 0.8. Therefore, the payoffs of player A depends on the probability of player B. Another example, the expected payoffs of player B depends on the probability of player A. So you look at the left-hand side and you see the probability of player A to go to university is 0.9. And if player B go to university and player A goes to university, player B will get 100 YouTubes. But expected payoffs or the payoffs adjusted by the probability will be 100 YouTubes. This is the full utilities that we can get times the probability of player A going to university, which is 0.9. Therefore, 100 times 0.9 is 90. So this is the expected payoff of player B if B goes to university. Here, in the second cell, you see that if player A goes to the airport, but player B goes to the university, you see that we have minus 100 YouTubes as the payoff, and it is the probability of 0.8. So it is 80% that B will go to the university if A goes to the airport, and it is 80% that B will go to university. It means that A tends to lose 100 YouTubes, but with the probability of just 0.8. So A can expect that he or she may lose 80 YouTubes. On the screen it is minus 80. So this is the expected payoff of A if A goes to the airport but B goes to the university. Here you see the expected payoff of B. If B goes to university and A goes to the airport, B will lose 100 YouTubes for the full payoffs. But just only the probability of 0.1 or just 10% that A will go to the airport. Therefore, B can expect that he or she will lose just only 10 YouTubes or minus 10. For the calculation of minus 100 YouTubes times the probability of 0.1. So you see again that expected payoffs of one player depends on the probability of another player. Here we turn to the third cell. The expected payoff of A if A goes to the airport, and then if A goes to the airport, he or she will gain 100 YouTubes. If B goes to the airport too. But B will go to the airport with the probability of just 0.2 or just 20%. Therefore, A can expect the return or the payoffs just only 100 times 20%. It is 20. You see that here the expected payoff of B. If B goes to the airport too and A goes to the airport, B will gain 100 U-turns, but with a probability of just how much? 0.1, 10%. Therefore, B can expect to gain just only 10, which is 100 times 0.1. You see that the name expected payoffs means that A can expect the gain or the lose by the full payoffs times the probability. And B can also expect the payoffs by multiplying the full payoffs with the probability. Here it is the meaning of expected payoffs, because both players can expect their payoffs. Now we turn to the last cell. We see that if A goes to university but B goes to the airport, of course A will lose 100 U-turns, but with the probability of just 0.2. Therefore, A will lose. A can expect to lose 20 U-turns. And if B goes to the airport but A goes to the university, B will lose 2 minus 100 U-turns, but with the probability of 90%. So B can expect that he or she will lose 90 U-turns. We come to write the expected payoffs into the matrix instead of the full payoffs. You see that now it is not 100 and minus 100, but the expected payoffs that we have calculated in the previous screen. You see that we have to compare. Now look at player A. Player A compares the payoffs. We have 4 payoffs for player A. Here, going to university and going to university, player A will get 80 U-turns. If player A goes to university and B goes to the airport, then minus 20. If player A goes to the airport and player B goes to university, minus 80. And player A goes to the airport and B goes to the airport, plus 20. Which one is the highest? The highest expected payoffs of A. So you see 80 minus 80 minus 20 and 20. So 80 is the highest. We maximize the expected payoffs. Therefore, player A will go to university because he or she can expect the highest payoffs. Now we turn to player B. Player B compares his or her payoffs, which is 90 minus 90 minus 10 and 10. Which one is the highest? Of course, 90 is the highest. Therefore, player B will decide to go to university because of he or she can expect the highest payoffs. So you see, when player A decides to go to university and player B also decides to go to university, they meet each other in the end, and we recall the original payoffs of 100 and 100. A will get 100 and B will get 100 U-turns. And the equilibrium, the answer of this game is in the bracket. You see university and university. It means that A will choose to go to university and B will choose to go to the university. They meet each other and the payoffs equals to in the bracket. So you see 100 and 100. A will get 100 and B will get 100. This is the solution of the game. And we call it the focal point equilibrium, as Thomas Schelling initiated and suggested us to use the focal point equilibrium to solve the game with more than one Nash equilibrium. Now, we look at the game number 3, Catch Me If You Can. It is the game between police and the thief. You see that they don't want to meet each other, especially the thief don't want to meet the police. But the police want to meet the thief. You see that we have two strategies, going to town and going to forest. If police goes to town and the thief goes to town, they meet, and police will get 500 U-tunes because they can arrest the thief. But the thief will lose minus 500 U-tunes because he or she will be arrested. So we have one side that get positive payoffs and another side get negative payoffs. You see, if they don't meet, for example, police goes to town and the thief goes to the forest, then the police cannot arrest the thieves. The thieves has positive payoffs of 500 U-tunes, but the police must be punished because he or she cannot catch the thief. Then the police will be punished with sadness by 500 U-tunes or minus 500. You see, in other payoffs, if police goes to the forest and the thief goes to town, then you see that it is minus 500 for the police and 500 for the thieves because the thief will go away and will not be arrested. Good for the thief. But if the police goes to the forest and the thief goes to the forest too, then this is good for the police, and the police will catch the thief and the police will get 500 U-tunes while the thief will lose 500 U-tunes. This is game number 3. Catch me if you can. You can notice that this is the zero-sum game. When one side get positive outcome and another side get negative outcome, so the summation of the payoffs would be 0. If one side gets the positive payoffs, then another side will lose and get the negative payoffs. This is called the zero-sum game. So you see, in all the cells of the payoffs, the summation of payoffs of A and payoffs of B, or payoffs of police and payoffs of the thief, will be 0. Here you can see that in stock market, when someone gets the profit and another one must have the loss. So money in one pocket goes to money in another pocket. This is zero-sum game. We recall the payoffs again, 500 and minus 500. Now you remember the payoffs. Now you see the ration function of the police first. So the police think if the thief goes to town, then he must compare 500 if he goes to town and minus 500 if he goes to the forest, And you see that it is better going to town because 500 is more than minus 500. And if the thief goes to the forest, the police think again. If he goes to town, he will lose 500. But if he goes to the forest, he will get 500. Therefore, the ration function of the police is if the thief goes to the forest, then the police goes to the forest too. Now, the ration function of the thief. If police goes to town, the thief don't want to meet the police, then the thief will go to the forest. And if the police goes to the forest, then the thief will go to town to escape. Here we see the comparison of the ration functions. You see that now we have no place that ration function number 1 stays together, and we have no place that ration function number 2 stays together. You see that ration function number 1 stays in 2 cells and ration function number 2 stays in 2 cells. So there are no matching between the ration functions, so there is no Nash equilibrium. In this situation, comparing to game number 2, you see that number 1 stays together in 1 cell and number 2 stays together in 1 cell. But this is not the case of game number 3. You see that they are separate to each other. And there is no pair of the ration function in the same cell. So there is no Nash equilibrium in this game. You can see that if police goes to town, then thief goes to the forest. And if police goes to the forest, then thief goes to town. So you cannot find each other here. And if police goes to the forest, then thieves go to town. And police goes to town, then thieves go to the forest. And then you may think of, then thief goes to the forest, and then the police goes to the forest, and then thief goes to town. So you cannot match the ration functions. It is not smooth and flow smoothly like in game number 2 that you can repeat it forever. But here you cannot find the flow, you cannot find the repeat. So it is not the Nash equilibrium because you cannot match the ration functions. Therefore, there are no place that they will meet each other, and there is no answer whether they meet each other or not. Here we assign the probability. When there is no Nash equilibrium, we assign the probability, and we think that the thief will go to town with the probability of 0.1, and he or she will go to the forest with the probability of 0.9. Now we assign the probability of police too. Here the probability of going to town of the police is 0.4, and the probability of going to forest is 0.6. Why? This is just the assumption, but we have some reasons behind that. The thieves may think that going to town is more risky because other people may recognize him or her. Therefore, he or she will choose to go to the forest where no one is there. And the police think, it is easier to go to town, but it may be better to go to the forest. So in fact, he or she think of 50-50, but place the more weight to go to the forest. but still think of going to town. So in his mind, he's like 50-50. He cannot choose whether to go to the town or go to the forest. But okay, yeah, he think of the forest more than the town. Then the probability of 0.6 is for the forest and 0.4 is for the town. Now we calculate the expected payoffs of the police and the thieves, and here we see that the expected payoff of the police if the thief goes to town, depending on the property of the thief, so it is 500 if he can catch the thief times 0.1, which is the probability of the thief going to town, then it is 50. And for the thief, he will lose 500, but the probability of just 0.4. Using the probability of the police, you see that now we have just only minus 200. And here, the second cell, we calculate the expected payoffs again, and we see that the expected payoff of the police if the thief goes to town is that minus 50. But expected payoff of the thief if police goes to the forest is 300. Can you explain why we calculate expected payoff like this? You see that the police expected that if the police goes to the forest and the thief goes to town, he will lose 500, but with the probability of just 10%. Then the expected payoff is just minus 50. And the thief expected that if he goes to the town and the police goes to the forest, he will gain 500 with the probability of 60%. So he will gain 300. Now, if the police goes to the forest and the thief goes to the forest too, then the police will gain 500 because he can catch the thief with the probability of 90%. Then the police will gain 450 U-tunes. But for the thief, he expects that if he goes to the forest and the police goes to the forest too, he will lose 500 with a probability of 60%. Then he knows or he expects that he will lose 300 U-tunes. And for the last cell, the expected payoff of the police if he goes to the town and the thief goes to the forest, he will lose 500 with a probability of 90%, which is the expected payoff minus 450 U-tunes. And the expected payoff of the thief, when the police goes to town, he will escape and he gains 500 with a probability of 0.4, 40%. Therefore, he expects that he will gain 200 U-tunes. Now, I ask you, who assigned the probabilities? You or teachers or who? So you see that this is the probability in the mind of the players. The police expect that the thief will go to town with probability of 0.1, and he expects that the thief will go to forest with the probability of 0.9. He reads the thief's mind. He expects the probabilities of the thief. The thief may think like that, and the police reads the mind of the thief. Here is the secret of game theory: reading the mind of other player. The thief reads the mind of the police. He knows that the police is somehow 50-50 to choose the town or to choose the forest, but he knows that the police may place the higher weight for the forest. Therefore, he expects that the police going to the forest with a probability of 60% and going to town with 40%. So this is reading the mind of the police by the thief. It is the thought of the police, but the thief reads that thought, read that mind. It is like the game theory that we call I know you, you know me, and I know that you know me, and you know that I know you. This is the game theory. Very interesting. The players know each other, and they know that the other side knows each other too. Here, we write the expected payoffs or the adjusted payoffs by the probability instead of the original payoffs. And you see that the police will choose between 50 minus 50 minus 450 and 450. So what is the highest expected payoffs? Of course, it is 450. So the police will go to the forest. This is the decision of the police to choose the highest expected payoffs because he or she can expect the highest outcome of his action. If he goes to town, he expects that the highest outcome is just 50. But if he goes to the forest, then he expects that the outcome is 450. And the thief, he compares between minus 200, 200, 300 and minus 300. And he makes the decision to go to town because of the highest expected payoffs. You see that if he goes to town, he expects that the highest payoff he will get is 300. But if he goes to the forest, the highest expected payoff is just 200. Therefore, going to town is the better choice. He or she will make decision to go to town. So the equilibrium is police goes to the forest and thieves goes to town. And we see that the original payoff states that the police will lose 500 and the thief will gain 500 U-tunes. So the thief escapes. And the police cannot catch the thief. So you see on the bottom of the screen, the equilibrium is at police going to the forest and the thief goes to town. And the payoffs record the original payoffs. You must answer with the original payoffs, not the expected payoffs. This is very careful. You must be very careful about this. So the payoffs, then the police will get minus 500 or lose 500 U-tunes, and the thief will gain 500 U-tunes instead. So you may remember that this is a zero-sum game. Now, we are at the end of the class, and what we have learned in this class. First, we have the mixed strategy, and the mixed strategy occurs when there are more than one Nash equilibrium or there is no Nash equilibrium at all. Second, the mixed strategy can be solved by the focal point equilibrium suggested by Thomas Schelling. And third, the focal point equilibrium can be found by maximizing the expected payoffs of each player, which is the payoffs adjusted by probabilities. So you have assigned the probabilities and calculate the expected payoffs of each player, and then you find the highest expected payoffs of each player, and that is the focal point equilibrium and the solution of the game. I have the challenge for you. In game number 3, catch me if you can. Can you find the probabilities of the police and the thief that make the game ends up without the focal point equilibrium. So you answer the property of the police going to town is how much, and then the property of the police going to the forest is how much, and also the property of the thief going to town and the property of thief going to the forest. And with these probabilities, you cannot find the focal point equilibrium. This is the challenge. Recall the original payoffs here, and you add the number of probability, and you make the game cannot be solved. Very challenging. Here, we are at the end of the class, and I would like to thank you very much for coming to the class today. I hope you enjoyed the class, and then see you again in next class. 再见 Goodbye สวัสดีครับ